Hey guys, this week we're going to start a new section. In this section we're going to be covering a lot of chemical reactions. Now the next 2 weeks we'll be covering photosynthesis and cellular respiration, which are two really important chemical reactions that are important for any ecosystem. Photosynthesis and cellular respiration are going to occur in plants, and only cellular respiration is going to occur within animals. This week, though, I wanted to cover the basis of what chemistry is, just to give you guys a refresher so that photosynthesis and cellular respiration hopefully makes a little bit more sense. So we will be covering Chapter 2 and a little bit of Chapter 3. So everything on Earth is made out of matter, and matter refers to anything that takes up space and has weight. Mass can exist as a solid, liquid, or gas, and all matter is going to be composed of elements, whether it's a single element like oxygen gas, or whether it is multiple elements in one, like water, which contains both hydrogen and oxygen. There are only 92 naturally occurring elements, but 118 elements are found on the periodic table. Elements 61, 85, 93 through 118 were all created in a lab beginning in the 1940s because two machines called nuclear reactors and particle accelerators were created. So scientists were able to use these to create new elements. However, we are only going to be focusing on two main ones, carbon and hydrogen. But just know that all living things are going to contain carbon, hydrogen, nitrogen, and oxygen. About 96% of most plants and animals are going to be made up of these four elements. In the human body, oxygen makes up about 65%, carbon makes up about 18%, hydrogen makes up about 10%, and nitrogen makes up about 3%. Calcium and phosphorus make up about 1%, and then the rest of the body is made up of trace elements. All of the aforementioned elements are made up of atoms. Each atom has an atomic symbol, which doesn't always correspond to its English name, but instead to its Latin name. For example, the English name for sodium is sodium, but its atomic symbol is Na, which of course there is no N or A in sodium. Instead, the Na refers to its Latin name, which is natrium, spelled Natrium. Every atom is made up of a combination of neutrons, protons, and electrons. Electrons will have a neutral charge, protons have a positive charge, and then electrons have a negative charge. The number of protons and neutrons found in the nucleus of an atom makes up its atomic weight. The number of electrons doesn't have an effect on the mass because the electrons hardly weigh, the electrons hardly weigh anything. So most of the mass is going to be found in the nucleus of an atom. So here you can see the structure of an atom. All the mass of the atom is going to be found in the nucleus here, which contains those protons and electrons. The nucleus will have a positive charge because the protons have a positive charge, and the neutrons contain no charge at all. An element is going to be determined by the amount of protons it has. If the amount of protons changes, then the element will change. However, if the amount of neutrons and the amount of electron changes, the element is still going to stay the same. Because opposites attract, the electrons are going to be flowing around the nucleus in something called an electron cloud. And all of those electrons are going to be organized into different electron shells or orbitals. Most of the time though, I'm just going to refer to them as electron shells. The first electron shell, the one closest to the nucleus, only has room for 2 electrons, as shown in picture B right here. So here we have our nucleus. And that first shell has room for 2 electrons. So this particular element is helium, and helium only has 2 electrons. And because this first shell only has room for 2 electrons, and there's 2 electrons here, helium is a stable element. So in other words, as long as the electron shell is full, then the element itself, or the atom itself, will be stable. If the outer electron shell is not filled, then that atom will be chemically unstable and is going to react in some type of way. The amount of electrons found in that outer shell is going to determine how it reacts in a chemical reaction. So there's going to be 2 numbers for each element on the periodic table. The top number is the atomic number, which tells you how many protons the element has. Generally, the amount of electrons that an atom has will equal the amount of protons it has. The bottom number refers to the atomic mass, which again is just the addition of the amount of protons and neutrons that that element has in the nucleus. If you want to figure out the amount of neutrons that an atom has, you're going to want to subtract the atomic number from the atomic mass. Or, in other words, you're going to minus the amount of protons that the atom has from the atomic mass to find out the number of neutrons. So all of the elements are arranged in the periodic table by the amount of protons that they have. This creates a pattern of both chemical and physical characteristics of the elements. Elements that are in the same column or groups tend to react the same way in a chemical reaction. So here you can see a very simplified version of a periodic table. We have our groups here, which just refers to the columns, and then our periods, which refers to the rows that the different elements are in. All the elements in groups 1, 2, and 3 are called metals, except for hydrogen, which is referred to as a gas. All the elements in groups 4, 5, and 6 are called nonmetals. The groups in 1, 2, and 3 will all give away their electrons in a chemical reaction. All of the elements in groups 4, 5, and 6 generally share their electrons in a chemical reaction. All of the elements in group 7 generally are going to take electrons in a chemical reaction. And then all of the elements in group 8 are referred to as noble gases and will not give, take, or share any of their electrons. That is because all of the elements in group 8 already have a full outer shell, and so they are chemically stable and are not going to react with any other element. Each of the group numbers will tell you how many electrons are in the outer shell of the element, and the periods generally will tell you how many electron shells that particular atom has. So helium here, helium is in period 1, which tells us that there is only 1 electron shell, and its atomic, even though it is in group 8, its atomic number is 2, and so there's only 2 electrons in its outer shell. It is, however, in group 8, since it's a stable atom, and it will not chemically react with others. This is why we use helium to fill up balloons instead of hydrogen. See here, argon, on the other hand, is in period 3, and so it's going to have 3 electron shells, and it's in group 8. So again, this tells us that there's going to be 8 electrons in its outer shell. So it again is stable and will not be chemically active. Boron is going to have 2 electron shells, and there's going to be 3 electrons in its outer shell. So because it doesn't have a full 8 electrons in its outer shell, this does tell us that it is chemically reactive and will want to react with another element so that it can form a compound and become stable to get a full outer shell. So again, in order for an element to be an element, the number of protons must stay the same. However, the number of neutrons or electrons can change, and it will still be the same element. When an element changes the amount of neutron it has, it is now called an isotope of that element. Because the number of neutrons have changed, the atomic mass has also changed. Generally, the new atomic mass will be written in the upper left-hand corner of the atomic symbol. Isotopes are very useful in research and in medicine. It can be used as something called a tracer, like if someone is getting a PET scan. Because a tracer emits radiation, machines can track where that particular atom travels in the body. Therefore, isotopes are also used to study the role certain atoms and molecules play in the body. Isotopes, though, need to be used with caution since they are radioactive and because they can cause cancer in the body due to cell damage. So PET scan stands for positron emission tomography. PET scans are used to determine the activity level of different areas of the brain. A radioactively labeled glucose tracer that emits a positron, a positron is a subatomic particle that is the opposite of an electron, is injected into the body. Positrons emit a small amount of radiation, which will be detected by the monitors and analyzed by the computer. The result is a colorful image, like the one off to the right-hand side, which shows which tissues took up that glucose and thus are metabolically active. A number of conditions, such as tumors, Alzheimer's disease, and epilepsy may be detected in PET scans. And if I remember correctly, I believe it is the red parts that indicate which part of the brain is not working. So all of the electrons around a nucleus are constantly moving. It is hard to pinpoint the exact location of any one electron. The electrons are arranged around the nucleus in those electron shells that I was telling you guys about. 2 electrons are going to go into that first shell, while 8 electrons are going to go in each additional shell. The closer a shell is to the nucleus, the less energy those electrons have. And because they have less energy, they are usually not going to be involved in the chemical reaction. Generally, it's just going to be those electrons in the outermost shells that are going to be involved in the chemical reaction because they have the most energy. The group number will tell you the amount of electrons that are in the outer shell, and therefore the amount of electrons that are involved in the chemical reaction that that element takes place in. So every atom strives for a full outer shell, and this outer shell is also called a valence shell. Depending on the amount of electrons in the outer shell, will determine if the element will give, take, or share its electrons. Thus, the number of electrons an atom has determines the chemical properties of that atom. So here are the atomic structures for hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. The number of electrons each element has are arranged into the different shells surrounding the nucleus. The closer the shells are to the nucleus, the less energy they're going to have, and so the less chemically active they are. However, the further away the electrons are from the nucleus, the more energy they have, and so the more chemically active they are. That is why only the electrons in the outer shell are going to be involved in the chemical reaction those elements undergo. When atoms chemically react, they form molecules. When there are more than one element in the molecule, it is called a compound. Oxygen gas would be considered a molecule, but not a compound, since we only have one element in that molecule. While carbon dioxide, on the other hand, would be considered a molecule and a compound. When atoms give or take electrons, they are said to be forming an ionic bond. When atoms share electrons, they are said to be creating a covalent bond. So ionic bonding happens when two atoms are held together by the attraction between opposite charges. And this happens when one atom gives up an electron and another atom takes an electron. So for example, sodium will have one electron in its outer shell, or its valence shell, and because it's easier for it to give away its electron, it's going to do so in order to become a stable element. And when it gives away that one electron, it's now going to have a positive charge. When chlorine takes that one electron from sodium, it is now going to have a negative charge. So those opposite charges are going to attract sodium and chlorine together, forming that ionic bond. Ionic compounds often are called salts. So sodium chloride, common table salt. Another example of salt is potassium chloride, which can be an alternative for people to use to season their food if for some reason they can't have sodium chloride. So here you can see the chemical reaction that is happening between sodium and chlorine. Sodium only has 1 electron in its outer shell, and chlorine is going to have 7 electrons in its outer shell. Again, all any atom wants is to have a full outer shell so that it is stable. So it's a lot easier for sodium to get rid of that 1 electron to have a full outer shell to be stable. Chlorine, though, all it needs is just 1 electron. So it's going to be a lot easier for it to take that 1 electron to fill its outer shell. So once that happens, then both atoms are going to be happy, and because they both have that full outer shell. However, now sodium is going to have a positive charge, and chlorine is going to have a negative charge. And these two opposite charges are what attract them to each other, forming that ionic bond, allowing them to be a molecule. So with covalent bonding, electrons are going to be shared rather than taken or given away. Therefore, no ions are going to be formed. Instead, the orbitals of the 2 electrons now overlap, in this case of hydrogen gas, as you guys can see here. So both electrons are going to fill the shells of both atoms. When writing the structural formula, as shown here, one line between the 2 atoms indicates that 1 pair of electrons is being shared between those 2 atoms. If there are going to be 2 lines between the atoms, this indicates that there are 2 pairs or 4 electrons that are shared between those 2 atoms. And the molecular formula just indicates the molecular formula shown here indicates the particular elements that are in that compound, and then the amount of atoms of each element that are in that compound. So in hydrogen gas, we just have hydrogen, and each hydrogen molecule contains 2 atoms. When elements share 2 electrons, like in hydrogen gas here, it is going to be called a double covalent bond. The structural formula will have 2 lines between the 2 atomic numbers, indicating that they are sharing 2 pairs of electrons. Carbon is going to be one of the most important elements in the world because it is able to form 4 covalent bonds with up to 4 different elements. Also because of this, carbon can be shaped in many different ways, like with the carbon chains found in lipids. Because of the chemical properties of carbon, it is found in every biological molecule. So here you can see an unsaturated fat, and unsaturated fat is a type of lipid, which contains fatty acid tails, which the fatty acid tails are just a string of carbons, and the carbons are little black dots here, with a bunch of hydrogen molecules attached to them, and the hydrogen molecules are the white dots. As you guys can see, carbon has room for 4 different covalent bonds. So here it is covalently bonded to 1 carbon atom. It is covalently bonded to 1 hydrogen atom. And this one is going to be doubly covalent bonded to this carbon atom right here. The way a carbon is bonded to the different molecules it's attached to will affect the shape of that particular molecule. So here we have an unsaturated fat, which just means it is unsaturated in hydrogen. Or in other words, it contains double bonds with the different carbon atoms here. This will affect the structure at room temperature. So all unsaturated fats are going to be liquid at room temperature because of these double bonds. These double bonds create kinks in the fatty acid tails, and so the fatty acid tails can't lay on top of each other smoothly, and so they just kind of create a jumbled mess. And so they are liquid at room temperature. Saturated fats, on the other hand, the fatty acid tails are able to lay on top of each other nice and neatly. So all saturated fats are going to be solid at room temperature, like butter here. Notice how there are no double bonds in these fatty acid tails. Instead, they are saturated in hydrogen. Trans fats are also solid at room temperature. This is because the fatty acid tails are also flat like saturated fats. However, you guys can still see that they have that double bond like unsaturated fats do. And this is because trans fats are unnatural. They are unsaturated fats that were bombarded with hydrogen molecules in the hopes of making them into saturated fats. This just allows the unsaturated fats to be solid at room temperature. And generally, a lot of the processed foods like donuts are going to contain those trans fats. So when elements chemically meet, they are called reactants. Anything that they produce is called products. And within a chemical equation, anything to the left of the arrow is going to be all the reactants, and anything to the right of the arrow is going to be all the products that are formed from the chemical reaction between the 2, 3, 4 reactants. So this particular chemical reaction is photosynthesis. So we have our reactants in this chemical reaction is carbon dioxide and water, and glucose and oxygen are going to be our products. You guys can tell these big numbers here are going to tell us the amount of carbon dioxide and the amount of water molecules that are going to be involved in our chemical reaction. If there is no number in front of our molecule, it just indicates that there's one molecule in that chemical reaction. So we have one molecule of glucose that is going to be produced from our 6 carbon dioxide molecules and 6 water molecules. And then we're also going to have 6 oxygen molecules that are going to be created from this chemical reaction here. So the chemical properties of any molecule will determine its physical properties, as can be seen in water. Water is the single most important molecule on Earth. All organisms are made up of about 70 to 90% of water. And water has unique properties that makes it a great life-supporting substance. And its physical properties, again, is determined by its chemical structure. So within a water molecule, 2 hydrogen atoms are sharing their electrons with 1 oxygen atom. Since they are sharing their electrons, they have a covalent bond. The covalent bond, though, within a water molecule is different than covalent bonds found in other molecules. This is because the size difference between the oxygen and the hydrogen atoms. So if the atoms involved in a covalent bond are different in size, then the electrons will drift closer to the larger atom than to the smaller atom. This is because the electronegativity of that larger atom. The bigger the atom is, the more electronegativity it has, and therefore the closer those electrons will be to that atom. You guys can think of electronegativity as gravity. The bigger a planet is, the more gravity it will have. The closer the moons will be toward that planet. In the same way, the electrons will be closer to the larger atoms. The bigger atom, oxygen, will have the negative charge, while the smaller atom, hydrogen, will have the positive charge. And they are now attracted to each other. So hydrogen molecules are going to be attracted to the oxygen molecules of other water molecules. This creates a hydrogen bond. And the hydrogen bond are weaker bonds that are going to bind the different water molecules together, and they will give water molecules 6 different properties. As you guys can see here, we have our different water molecules. So we have our oxygen molecule here, and we have our two hydrogen molecules here. Because of the size difference of our oxygen molecule in comparison to the hydrogen molecule, the electrons are going to be closer to that oxygen molecule, giving the oxygen a negative charge and the hydrogen atoms a positive charge. And just like in an ionic bonding, those two different charges will be attracted to each other, forming this weak bond here called a hydrogen bond. And again, causing water to have different properties that makes it really important within plants and animals. So the 6 different properties that hydrogen bonds give to water is solvency, cohesion and adhesion, high surface tension, high heat capacity, high heat of vaporization, and varying densities. There are many chemical reactions that need to take place in the body, and water is a really good environment for these chemical reactions to take place in, and this is called solvency. Due to the polarity and the hydrogen bonding, water is able to dissolve many polar substances. This is because like dissolves like. So water will be able to dissolve any hydrophilic molecules. Hydrophilic meaning water loving, and hydrophilic molecules will also be polar as well. Hydrophobic molecules, on the other hand, or nonpolar molecules, will not dissociate in water. An example of a hydrophilic molecule that will dissociate in water is sodium chloride. And so when these molecules dissolve in water, they free up those atoms to chemical react with other molecules in the body, which is again why water is just such a good place for chemical reactions to take place in. As discussed before, the polarity of water molecules allows them to stick together. This is called cohesion. The polarity of water molecules allows it to stick to other polar substances, like the inside of the blood vessel, or the vascular tissue found in plants called the xylem or the phloem, and this is called adhesion. These properties allow a constant flow of water in one direction in a blood vessel and the vascular tissue of a tree. Water molecules adhere to the wall of the vessel, and water molecules cohere to each other, allowing one constant flow of water, like a river. The hydrogen bonds in between the water molecules also gives it a high surface tension, which different insects are able to take advantage of, like this water strider here. Water striders also maintain buoyancy by having little pockets of air underneath their feet, and some water striders even secrete a nonpolar wax, which further aids in it being able to walk across water. Water is also able to have a high heat capacity, and this particular property is really important in maintaining life on Earth. All the chemical reactions in our body release a lot of heat, and if our body didn't contain water, then all of that heat would cause us to die. The water absorbs the heat and allows us to maintain a certain body temperature. And then the last property is a heat of vaporization, which just means that it takes a great deal of energy to break the bonds for evaporation. And because it takes a lot of heat to break those hydrogen bonds, a lot of heat is also released as those hydrogen bonds are broken or as water evaporates. If the temperature in our body reaches a certain point, that heat causes the water in our body to evaporate, which is what causes sweat, and is also our body's way of helping cool down our body. Another property that hydrogen bonds gives water is its varying density as at its different states of matter. Water is a lot less dense as a solid than it is as a liquid, which is different than other substances. And because water is less dense as a solid, this allows ice to float within liquid drinks. This is really important to help maintain life in a body of water, because that layer of ice insulates the rest of the body of water and keeps it warm enough to sustain life within that body of water. The arrangement and spacing of the water molecules when they freeze is what causes ice to be less dense than water. Notice how the individual water molecules are further apart when it is a solid versus when it is a liquid. The water molecules are a lot closer together when they are a liquid, allowing them or causing them to be more dense. Whether a liquid is acidic or basic is going to be determined by the amount of hydrogen or hydroxide ions it releases in any liquid. Water is not acidic or basic. Instead, it has a neutral pH or a pH of 7, and this is because it will release an equal amount of hydrogen and hydroxide ions. At a neutral pH, there will be an even number of hydroxide and hydrogen ions. Acids are going to have more hydrogen ions than hydroxide ions. So this means anytime acids are placed in water and they dissolve, they're going to release more hydrogen ions into that liquid, causing it to be an acid. The strength of that acid is going to be determined by the amount of hydrogen ions that that atom releases. Some examples of acids are lemon juice, vinegar, and coffee. Basic solutions, on the other hand, are going to have more hydroxide ions than hydrogen ions. And the strength of that base is going to be determined by the amount of hydroxide ions it releases when it is placed within water. Some examples of basic solutions include milk of magnesia and ammonia. So the pH the pH scale ranges from 0 to 14. And it's a mathematical way to indicate the number of hydrogen and hydroxide ions in a solution. A neutral pH at number 7 means that there is going to be an even number of hydrogen and hydroxide ions. A pH between 0 to 6 is going to be acidic, and it means there's going to be more hydrogen ions than hydroxide ions. And a pH between 8 and 14 is going to be basic, and it means there's going to be more hydroxide ions than there are hydrogen ions. The further up the scale you go, the further down the scale you go, the more acidic the liquid becomes, and the further up the scale you go, the more basic it becomes. Each number represents either a tenfold increase or a tenfold decrease in the amount of hydrogen or hydroxide ions, just depending on the way you go. So a pH of 2 is going to have 10 times the amount of hydrogen ions as a pH of 3, while a pH of 12 is going to have 10 times the amount of hydroxide ions as a pH of 11. Because we consume many substances that are more basic or acidic, our body needs to be able to take up excess hydrogen and hydroxide ions so that our body maintains a neutral pH between 7.35 and 7.45. This allows the human body to maintain homeostasis. One way the body keeps a neutral pH is by eliminating excess hydrogen and hydroxide ions. People who eat meat tend to have a more acidic urine because meat contains a high amount of hydrogen ions, while vegetarians tend to have more alkaline urine since vegetables contain more hydroxide ions. Our respiratory system also helps maintain our blood, our neutral blood pH. When you hold your breath, your blood becomes more acidic. However, when you breathe out, your blood pH returns to normal. If our blood pH becomes either too acidic or too basic, it can cause some really bad medical problems. Acidosis occurs when the body is unable to buffer high amounts of hydrogen ions within the blood. Some symptoms include headaches, muscular weakness, diarrhea, nausea, coughing, and arrhythmia, which is a high heart rate. So now we're going to move on to organic chemistry, which is chemistry that happens within animals and plants. Because organic chemistry focuses mainly on carbon and hydrogen. So because of the special chemical properties of carbon, it is the main element that is focused on when looking at organic molecules. All organic molecules has a combination of carbon and hydrogen ions. Molecules with only carbon or hydrogen are not considered organic. Organic molecules have a variety of shapes, as we discussed a little bit earlier, since carbon is able to covalently bond with 4 different molecules, allowing it to take up several different shapes. And because it does have several different shapes, organic molecules can have a lot of different functions. Carbohydrates form fibers that provide supports to plants. Proteins help maintain the walls of bacteria. Lipids, such as oil, are used as energy storage in plants. And then nucleic acids form DNA, which of course acts to store the genetic information within plants and animals. So the carbon atom has a total of 6 electrons, and 4 of those electrons is going to be in its outer shell, and so are the ones that are going to be chemically active. Carbon can bond with up to 4 different kinds of atoms of various different kinds of elements. Most of the times in organic molecules, carbon is going to be bonded to hydrogen, nitrogen, or oxygen. Within a lot of different organic molecules, you're going to find hydrocarbon chains, which are just going to be chains of carbon bonded to hydrogen atoms. And several different organic molecules are going to be isomers of each other, which just means that they're going to contain the same molecular formula or the same amount of the same kinds of elements and the same amount of atoms. However, the chemical structure is going to be different, and so the chemical properties are going to be different from each other. As shown here, carbon can take on many different shapes because it is able to bond up to 4 different atoms. It can form single chains, branched chains. It can also form rings that contain both single bonds or double bonds, like those found in sugar. All biological molecules are made of carbon chains, but it is the functional group that's attached to it that will identify the biological molecule as one or the other. The functional group always has the same chemical structure, and so will always react the same way in each reaction. As a result, the functional group largely determines how that biological molecule will behave inside the body. Here's a couple of different functional groups that you can find in biological molecules. The hydroxyl group here are found in alcohols and sugars. The amino group is going to be found in amino acids and proteins. And then the phosphate group are going to be found in ATP, which is cellular energy, or in nucleic acids that's found in DNA and RNA.